Hello and welcome back. This is Jonathan Gardner. We're covering section 1.6 of Daniel V. Schroeder's An Introduction to Thermal Physics. And in the previous section, we went over the constant pressure and the constant value heat capacities. In this section, we're going to continue the section by discussing latent heat and enthalpy. And he starts off talking about phase transformations. Okay. What are phase transformations? Well, as you should know, and if you don't know, now you will. If you have a cup of water, and inside that water is ice, so you have an ice-water mixture, and you've allowed the water and the ice to come to thermal equilibrium, which really doesn't take that long, okay? Then you know that this water is about 0 degrees centigrade, okay, or 32 degrees Fahrenheit, depending on which way you roll, okay? Now, if I were to add heat to this system, if I were to take this and put it on my stove and apply heat, then what I would see is the ice would start to melt. However, the temperature would remain constant. Okay, so if we were to calculate the heat capacity of this ice-water mixture, we can talk about the heat that we added and the change in the temperature. Well, we've added plenty of heat, but there's no change in temperature, and so this makes no sense, right? Now, he says this is equal to infinity, but really infinity is not supposed to be used this way. Infinity is a concept you use in limits, you use in sums and stuff like that. But so in this case, you can keep adding heat and there's no change in temperature, so the heat capacity is basically infinite or undefined, is what I would like to say. Okay. However, we still want to keep track of that heat for whatever purposes. And so we're going to talk about the latent heat. So the latent heat. This is given with an L, and it's defined to be the amount of heat added over the amount of mass that is changing in the transformation. Again, we have an ambiguous definition here because we don't know what the work is happening during this process, right? So we could be heating the ice water bath and it could be expanding in volume, but we're trying to keep the pressure constant, or we're trying to keep the volume constant. We don't know which one's doing what. We usually assume by convention that pressure is constant. Okay, because oftentimes the volume will change quite significantly, and the pressures, if you try to keep the volume the same, will be quite high. Okay, the latent heat for melting ice, so we want to melt ice. This is 333 joules per gram of ice. Okay, or we could calculate that using 80 calories per gram. Okay, so this is the latent energy of melting ice. Okay. The latent heat for boiling water, I'll just write it as a subscript here. This is quite a bit larger, 2,260 joules per gram, which is equal to 540 calories per gram. Okay, so how much energy does it take to raise water from 0 degrees Celsius to 100 degrees Celsius? The answer is about 100 calories per gram. So it takes about 100 calories per gram to raise that temperature that much. So it takes 3 times as much energy just to melt the ice, and it takes 22.5 times as much energy to boil that water off. Okay. There's a couple problems here. If you have 200 grams of tea that is boiling hot, so you just taken this straight off the stove after it's been whistling, how much ice should you add to bring it down to a comfortable sipping temperature of 65 degrees Celsius? Okay, and he says go ahead and assume the ice is not at 0 degrees Celsius but minus 15 degrees Celsius because you keep your freezer quite cold or whatever. And he gives you the heat capacity of ice, which is half a calorie per gram per degree centigrade. And then problem 148, when spring finally arrives in the mountains. So what he does in problem 148 is he talks about snow. It's half air, it's half ice. And he disregards any heat transfer due to a change in temperature in the atmosphere versus winter. Okay, and he only talks about the amount of sunlight that hits the snow. Okay, and he says 90% of it's reflected off, so you're only getting 10% of that energy actually into the ice itself and the air. Don't forget the air. The air is important. Okay, and the question is, how long will it take for the snowpack to last before it all melts? Okay. So you can do that calculation. You'll find some interesting results there. Next concept. The next concept he introduces is something called enthalpy. And this looks like entropy, but it's not entropy. And it actually, I think the concept of enthalpy arrived after entropy. So in enthalpy, we note that there are constant pressure processes everywhere, okay? And keeping track of the compression expansion work done during these processes can be tedious. And there's a trick that we can use so that we can do our calculations and get the right answer without thinking too hard about whether that energy is in the temperature or whether that energy is in the pressure and the volume, okay? So we define the constant, or not the constant, the value H is defined to be the internal energy of the system plus its pressure and its volume, okay? The interpretation of this is basically, this is the entire amount of energy you would need to create the object at all. So first you need to create the temperature, right, of the object, and then you would have to expand the object at a pressure until it finally comes to its final resting pressure and volume, okay? Another way to interpret this is what happens if you were to erase this object from existence, right? So there would be a vacuum created of a certain volume, and so the pressure that was around that object would have to fill in that gap, as well as you'd be losing that heat energy, basically, the temperature energy that disappears, okay? There's a cute little diagram here of a wizard creating a rabbit, okay? So we're going to play with enthalpy to see how we can use this to calculate changes to a system, okay? So if we start with an initial amount of enthalpy and then we add some more enthalpy, that's the same as U plus delta U, and P, because we're keeping pressure constant, V plus delta V, okay? And so we can rearrange our terms, so we get U plus PV plus delta U plus P delta V, okay? And so this term is obviously just H, right? And so we can calculate that when we add a little bit of heat or enthalpy to the system, we're going to see an increase in the internal energy of the system plus a change in volume at constant pressure, okay? So these two things will cause the enthalpy to increase. One is the temperature, or the internal energy of the system is increasing. And by internal energy, we have to keep in mind that this is not just temperature. It could also be chemical reactions that are happening within the substance. The enthalpy may also change due to an increase in the volume, but we're maintaining the pressure constant. So we're allowing this object to change its volume however it wants to, okay? Now keep in mind that according to the first law of thermodynamics, delta U is equal to Q plus W, okay? And what is the work? Well, the work is equal to our pressure times the change in volume plus any other type of work that might exist, okay? Of course, we have to remember that this is negative because when the pressure decreases, when the volume decreases, then we're seeing work added to the system. But when the volume increases, we're seeing work removed from the system. So if we combine this delta U, Q plus W, we get Q minus P delta V plus other work. Then we get P delta V here. And so we get Q plus other work, okay? So this change in the enthalpy tells you how much heat is added to the system, as well as what other work besides the change in volume and pressure has been done to it. If we were to calculate the CP for an object, we can use the enthalpy, the change in the enthalpy over the change in temperature held at constant pressure, and that will give us the right answer, okay? You should be able to see that this is exactly the same as equation 145, which is the equation that he derived when he was calculating the constant pressure heat capacity, but using the delta U's and delta V's, okay? So this is exactly the same. So we call CP, we call this the enthalpy capacity. And CV we call the energy capacity. You can look up the delta H values in chemistry books, and there's lots of tables of these delta H values because these are values that are actually useful when you're doing measurements in a laboratory, okay? For instance, if you look up in a table, it will tell you that for H2O, when you boil that water away, so 1 mole of water at 1 atmosphere is 40,660 joules. Okay, so since a mole of water is about 18 grams, okay, 16 grams of oxygen, 2 grams of hydrogen, this means that the change in enthalpy when you boil 1 gram of water should be 4,660 joules divided by 18 grams. And that gives you the 2260 joules per gram that you had earlier. Note that the work done on the water includes the work to increase the volume of the water as it boils away. Okay, so if we had 1 mole of water, so we have PV equals nRT, so we have 1 mole of water, and so the volume of that water is going to be RT over P. The amount of work that was done, the PV work, is equal to RT, which will give you 3,100 joules. So that's the amount of work done to increase the volume by pushing the atmosphere away. Okay, so of that 40,660 joules, 3,100 of that is used to increase the volume. Let's analyze a more complicated situation. In this case, we're going to take 1 molecule of hydrogen gas and 1/2 molecule of oxygen gas, and we're going to create 1 molecule of water. Okay, now chemists might be screaming at me right now saying just do 2 hydrogens and 1 oxygen and 2 waters. But I'm going to write it out this way. Okay, for each mole of water produced in this reaction, delta H is equal to minus 286 kilojoules. This is per mole. Okay, this is referred to as the enthalpy of formation. Now, some of this energy comes from the energy of changing the molecular configuration of these molecules. Other of the energy actually comes from the changing in the volume of the gas that they actually contain, right? So the hydrogen gas and the oxygen gas take up more volume than water would, especially in liquid form at room temperature. Okay. Now, a question you might have, and this is kind of critical to a lot of the problems that people have with understanding how energy works in real life, is can you extract the energy as, let's say, electrical or maybe mechanical? And what this is asking is if we can get the energy that's produced from this reaction and convert that to electrical energy, then we can use this to recharge our batteries, to power our homes or electrical vehicles. If we can get mechanical work out of it, however, we can use this energy to power motors that drive our cars. So we can have cars that produce water rather than carbon dioxide and things like that. Okay. Now, the answer is that we can get much of the energy out as beneficial work, but there are limits that we'll see in Chapter 5. Okay. Problem 149 is to walk through this scenario of making water and figure out what happens in terms of the internal energy of the system and what happens in terms of the collapsing atmosphere, how much work is done as the atmosphere collapses. Now, for his purposes, he says just consider the amount of volume that the liquid water takes is 0. It's very negligible. It's very small. Problem 150 says we're going to burn methane gas. So we start with CH4 in gas form. And we're going to take 2 oxygens in gas form. And we are going to burn that into carbon dioxide, which is also a gas, and to 2 water molecules as a gas, okay? And we are doing this at 298 degrees Kelvin. And we have temperatures that are pressures that are at 10 to the 5 pascals. And we're going to maintain these temperatures before and after. So in order to do this process, first, part A is we're going to convert the CH4 into graphite and hydrogen gas. And you can look at the data in the back of the book. And then problem B is we are going to form that into carbon dioxide gas and 2 moles of water. Okay, and you'll look up in the back of the book what that is. And then in part C, we will try to figure out the delta H just going straight from here to here. Problem D, how much heat is given off during the reaction, assuming that no other forms of work are done. So how would you calculate the heat that is lost during this process? So you'd obviously have to calculate the amount of work done and the amount of energy that's been added to the system. And then you would have the heat that would have to bring this all back to, the standard temperature pressure. Problem E says, what about the energy change during this reaction? And he says, for this, you can see if the answer is different based on whether H2O has negligible volume or whether it is the vapor. Problem F says, what if the sun were powered by this methane reaction? How long could it last before it consumed all of its methane and oxygen and converted that all into carbon dioxide and water? Okay. Problem 151, we are going to convert glucose, C6H12O6. We're going to add in some oxygen and we're going to produce carbon dioxide and water again. And this is a very interesting process because this is the reaction that our body generally uses when it's burning energy, right? So when you eat food and burn energy, this is basically what it's using most of the time. Problem 152 is we take a look at gasoline. So we have a gallon of gasoline, which is 3.8 liters, is about 31,000 kilocalories. And then we compare this with burning cornflakes, okay? And you can go look at the store for current prices, buying cornflakes versus buying gasoline. If you're not in the United States of America, the price of gasoline is probably much higher where you're at. Even in the United States, like where I live versus like Texas and different places, like in Texas, the price of gasoline is ridiculously cheap, even compared to where I live. So go ahead and use the price of gasoline that you can find. Then cornflakes, you can go to a website like Amazon. You can look up, how much would it cost for cornflakes, or you can go to a store like Walmart, for instance. Walmart will tell you how much cornflakes cost. Okay. There's the brand version. And then there's the off-brand version. I forget what the name is for Walmart's off-brand version of cornflakes. But yeah, you can go look up on their website to see what the price of that stuff is. And it's interesting to see whether it's better to burn cornflakes or whether it's better to burn gasoline. I think you'll find the answer may be surprising. Okay, 153. So look up the enthalpy of formation of atomic hydrogen in the back of the book. And the question is, what would it take to take a hydrogen molecule and break it up into 2 hydrogen atoms? How much energy would that take? Problem 154, a hiker who weighs 60 kilograms wants to climb to the top of Mount Ogden, wants to climb 5,000 vertical feet, 1,500 meters. So if this hiker is 25% efficient at converting chemical energy from food and into mechanical work, and all of that mechanical work is used to climb, how many bowls of cornflakes with 1 ounce, 100 kilocalories should the hiker eat before setting out? This is interesting. I don't know that hikers, I think when you're hiking, actually, you're using more of the fat burning process than the sugar burning process, but it all ends up pretty much the same. So question B is interesting. If she weren't shedding heat to the environment, how hot would she be by the time she got 3/4 of the way up? That's an interesting question. These are always fun physics questions to think about. And in problem C, we are taking the energy that would have warmed up her body, and we're using that to convert water into vapor. So the question is, how much water does she need to drink to maintain that process to keep herself cool? Okay, that's a pretty interesting question too. 155, last problem of this section. This problem looks at, so when you have orbits, you have something that's orbiting, like a planet that's orbiting around a star, or even 2 particles that are orbiting each other in a zero gravity system, right? The energy of this system, some of it's stored in the kinetic energy of the object that's orbiting, or the 2 objects that are orbiting each other, or however you want to do it. And the other energy is stored in the potential energy, right? So they're forming these gravity wells, basically. And as they fall down this gravity well, their potential energy drops, okay? And so you can calculate, based on standard orbital mechanics, the distance that they have from each other, the amount of energy that's in that distance, and the amount of energy and kinetic energy as well. If you have problems figuring that out, contact me on Discord. I'll help you out. Problem B says, what happens when you add energy? How would it come to an equilibrium state? What would that look like? The virial theorem tells us that the potential energy is -2 of the kinetic energy averaged, of course. Okay, and so if you were to add energy to the system, would the kinetic energy increase or decrease? And this is basically asking that if you were to have a wider orbit, is there more kinetic energy or less kinetic energy? Okay, and in C, we can say that a star is bound together with this gravitational potential, and so we're going to find the temperature of the star according to the energy of the star. Okay, now be very careful with your number signs. Okay, you're going to find that you're going to get an answer that may be surprising. In problem D, when he says dimensional analysis, what this means is you basically drop all the numbers and you look only at the units. Okay, so the mass is measured in kilograms, the radius is measured in meters, and the gravitational is a force per kilogram squared times distance squared. So force distance squared over kilogram squared because of, g m1 m2 over r squared. And then you should find that there is another constant that you need to multiply to make the dimensional analysis work. And in problem E is to estimate the average temperature of the sun with a mass of 2 times 10 to the 30 kilograms and a radius of 7 times 10 to the 8 meters, and assume that the sun is made entirely of protons and electrons. So hopefully you'll enjoy this problem. This one should be quite challenging. If you have any questions, of course, you can find me on Discord. I'd love to help. Guys, thanks for watching. Thanks for supporting this channel and sharing these videos with your friends. If there's any questions you have as I cover these topics, if there's like something in the chapter that doesn't make sense, please call out in the comments. I will try to make a better video. Maybe I'll replace the lecture with one that actually has the questions answered if it's an important question. Guys, I hope you enjoyed this. Take care and bye-bye.